So good afternoon, everyone. So today we have the pleasure to receive Adèle Ribeiro. So Adèle received her PhD degrees in computer science from the Institute of Mathematics and Statistics of the University of São Paulo, so at UFSCar-USP. So Adèle is a postdoctoral researcher in the Causal Artificial Intelligence Laboratory at Columbia University. Her research relies at the intersection of computer science, statistics, and artificial intelligence applied to healthcare. So today, Adèle is going to talk about causal effect identification in partially understood domains. So thank you again, Adèle, for accepting our invitation. And now it's up to you.
Thank you for the invitation. It's really a pleasure to be here. So today I'm going to speak about causal effect identification in partially understood domains. This is my work as a postdoc in the Causal Artificial Intelligence Lab at Columbia University. If you want to know a little bit more about my work, this is my webpage. So first, why causality? Why this is so important for us now? So causality is an essential component in the development of the new generation of artificial intelligence methods, because it allows a lot of capabilities. For example, first, effect identifiability. This means that we can identify or determine the effect of some unrealized interventions instead of just predicting an outcome. So this is the difference between association or correlation and causal relationships. Another important capability is about explainability. The current methods in artificial intelligence, they usually rely on just the observational distribution. I'm going to explain a little better what this means. And then the only thing that you can do based on this on these results is to do predictions, to make predictions about some phenomena. You cannot explain why the outcome is coming about. You cannot understand the mechanisms, the underlying mechanisms of the system. So causal reasoning allows us to explain or give explainability for these methods. Another hot topic in research is about fairness. Because this is just a particular case of explainability. Since you can explain how the mechanisms are given some outcome, you can explain if some outcome is given to some mechanisms of discrimination, and this includes some direct effect of discrimination or indirect mediated effects, indirected effects. So we can explain better why the results are being generated. And another important topic is about generalizability. This is also known as transportability, because sometimes you know the effect of an intervention in some population. For example, if you run or if you conduct a clinical trial, usually you are running this experiment for one specific population. So the results, they have internal validity. They are valid for that specific population. But if you want to transport or generalize such results to another different population, you need to understand the mechanisms and the disparities across all these populations to then ensure the validity of the causal effect in the external population. And finally, it's about data fusion. Data fusion, what I mean is like when we have different experiments or different observational studies, different data sets, and you want to combine them to then get a summary result about some phenomenon. And the language of causality allows us to combine different data sets, because you have the capability of providing a description about all the difference across all these data sets. So this is another, we say it's another dimension of causality, of the theory of causality. And today we are going to focus on effect identifiability. So how can we determine the effect of some interventions I'm going to emphasize this is unrealized intervention. So we don't conduct a clinical trial. We get observational data. So we collect data in a passive way. For example, if you go to a hospital, you just collect data there. You are not performing any intervention. And using this observational data, you want to infer some causal effects, some effects of as if we are performing an intervention. So the important, so this is a mantra that we all know, we are all familiar. So that correlation doesn't imply causation. So let's just read this this comic. Another huge study found no evidence that cell phones cause cancer. What was the WHO thinking? I think they just got it backward. What? Well, take a look. So they have this plot, and if you see that is like the total cancer incidence, it's increasing over the years. And after a few years, after 20 years, we observe another increasing of the cell phone users. So it seems, if just looking at this plot, that the cancer incidence is causing cell phone users. And then the guy says, "You are not. There are so many problems with that, with this interpretation. Just to be safe," the guy says, "I see. Until I see more data, I'm going to assume cancer causes cell phones." So the question here, is it true that we'll be able to decide this causal relationship just by collecting more data? Do you believe that this is true? This is just an association. So does this association imply causation? So how can we decide, is this mobile phone users is causing cancer, or it's the other way around, is cancer causing mobile phone? So in reality, this maybe neither. Maybe what is happening is that we have a different model causing this spurious association. For example, we usually have in mind a structural causal model. So the structural causal model is just the data generating model, is something that generates the data. And suppose that we have two variables, x and y, and also we have some unobserved variables that we are calling u. So all these u's are unobserved. We don't observe these values. And the variable x, for example, maybe I should show the graph. So suppose that x is the mobile phone use. And then the use of mobile phones is actually a function of this unobserved variable called technology. So the technology is allowing more users to buy or to make the cell phones more affordable. That's why the technology is a cause of the increasing of mobile phone users. And at the same time, this technology is also increasing the cancer incidence, but just because we are improving the diagnostic tools to detect cancer. So the y, the variable y, is a function of the same unobserved variable uxy. So that is a common hidden confounder, we say, that's causing this spurious association between the variable x and the variable y. So it's not like x causing y or y causing x. Actually, it can be something else. And this depends on the real, that's usually unknown, unlearning mechanisms. Now, in this case, it's just that the advances in technology over the years have made mobile phones more affordable and enhanced the diagnostic procedures for cancer. So how can I answer? So based on this observational data or these observations that we are making in the road, how can we answer this type of questions? Should I limit my cell phone use as a precaution against cancer? This is a decision-making question. So how can we answer the effect of an intervention of avoiding the use of cell phones as to reduce the incidence of cancer? So we need a new tool that's based in a causal inference to determine the effect or identify the effect of interventions. And then we can now make this distinction about prediction versus decision making. So again, we have this underlying structure causal model. And when we consider the model without performing any intervention, as we are, when we are collecting data from in these observational studies, we are usually collecting data from this pre-interventional structure causal model. So this is the data generating model. And there's nothing, this is as all the functions are as they are, as the nature created. So in this case, for example, x is a function of the u, x, y, and also a few of other unobserved variables. But collecting data from this observational world, so this is wrong. So this is from this pre-interventional distribution. We can only detect differences between conditioning on a variable. For example, the probability of y given x, in this case, will be different than the probability of y. So those two distributions are called observational distributions because they are coming from the observational world where no intervention is being performed. And then the only thing that we can do from this data that's been collected from this observational world, we can compute observational distributions or conditional probabilities, as we are seeing here. And the consequence is that when we have this difference, we have that x is correlated to y. This is the definition of correlation. When we have a difference between the probability of y given x as being different than probability of y, we say that they are correlated, or that x, conditioning on x, makes the probability of y change. So that's why y depends on x. But this is just correlation. And what we want is another world. It's called post-interventional world. And that is another model that describes this world where we have the intervention. And this model is where the variable x is fixed as a specific value x. We are changing, we are manually going there in the world and changing the variable x to be a fixed value x, small x. And we want to know what's the consequence on the variable y after having this intervention on x. So if we collect data from this post-interventional world, we can just do the same. We can see if the probability of y conditional on setting this variable x as small x is different or equal to the probability of y. And if we had this model in hand, we could just detect that these two probabilities in this case is the same, because the function of y doesn't depend on the variable x. So changing or setting the value of x as small x, that has no implications on the attribution of the value of the variable y. So we will see that making the intervention on x makes no difference in the observation of the variable y. And then we will see that x is not a cause of x. X is not a cause of y. So that's the interpretation of effect of interventions. But usually these models, these structural causal models, are unknown. We don't know what's the model that generates the data that we are collecting. So the beauty of the graphical theory of causation is that you can describe this model, the same structure causal model, as a causal diagram. So in this case, we know we can just describe the functions using arrows in a graph. So we know, for example, that x is a function of the variable u, x, y. That's why we have the I'm just putting this as a dashed variable because it's hidden, so we don't observe this variable, but we know that this variable exists, and this variable is a cause of y. The same thing is like the variable u, x, y is a cause of y. And now we want to see if this connection from x to y is actually a cause or a spurious association. So that's the question. So what's the effect of y, effects of x on y but given this causal diagram. So the task is now different. Instead of being relying on a structural causal model, we are now relying on a causal diagram. So we don't need to specify the form of the functions or the distribution of the variables. We just need to describe the graphical structure of the causal model. And now we want to do the same. Based on this diagram, we want to ask questions about, this should be pre-intervention, about the conditional probabilities in the observational world, and see if the X and Y are correlated. And also do the same thing, but observe after doing an intervention. So how can we compute the probabilities, the conditional probabilities, assuming now that the X is an intervention. And if you observe the causal diagram, the effect of setting the variable X as a specific set makes cutting all the arrows into X, because now X is no longer a function of the other variables. It's just, it's a constant. We are setting it as a small x. So that's the description of the interventional role, and we want to compute the effect coming from here. So that's the task. And now we in this case, we would be concluding that X is not a cause of Y. If you have any questions, you can ask me at any time. So what's the conclusion? The conclusion is that a causal diagram is just an encoder of structural knowledge. It's different than functional knowledge because we are just describing the structure using arrows and nodes of a graph. So given, just formalizing the construction of a causal diagram, given a structural causal model, so we don't know the causal model, so that's why it's in gray here, it's hidden. But the only thing that we need to know is about arguments of and functions of variables. So which variables are arguments of the functions of the other variables. So what's the induced causal diagram? So we just put nodes for every variable that we have in the system. And then for every time that a variable Vj appears as an argument of the function of the variable Vi, we are going to add an arrow from Vi to Vj. So for example, we add the arrow from X to M because X is an argument of the function of M. The same from M to Y. We add an arrow from M to Y because M is an argument of the function of Y. Now we add a bidirected arrow between two variables if they have, so we have two variables, Ui and Uj. They are the external or the hidden causes of the corresponding variables, Vi and Vj. So in this case, X, we have a Ux here because they are factors that are unobserved, but they are arguments of the variable X. This is the same for the Uxy. It's another hidden variable that's an argument of the function of X, and it's a cause of X. So every time that we have shared, so this unobserved variable is both argument of X, of the function of X, and also argument of the function of Y. So every time that this unobserved factor is shared between two variables, we are going to add a bidirected arrow between X and Y. This is what's written here. And then how can we do causal inferences then? So we start with a query. It's a research query, and this is denoted by the operator do. So if we want the effect of X on Y, is the effect of an intervention of setting the variable X as this small variable X, small value X on Y. So this is the notation, the do operation. The do operator is just denoting an intervention on a variable X. If we want the effect of X on Y, we usually need to compute the interventional distribution Py given to X. And given this intervention distribution, you can estimate the expected causal effect and so on. But this is the query, the research query when we are doing causal inference, applying causal inference tools. And the second input of this engine is the causal diagram, because it's encoding some causal constraints. And the third one is the data. So the conclusion, the lesson from here is that we cannot compute causal effects just from observational data. We need more information. And this other information is encoded in the causal diagram. We need this causal diagram to compute causal effects. So then we feed all these three inputs to the inference engine, and then we can have a yes or no answer. Sometimes the knowledge that we are encoding here in this causal diagram is not enough to compute to answer the query. So then we will have a no answer. But if the causal diagram is encoding sufficient knowledge to determine the causal effect, then we will have an expression that's only in terms of the distributions available. In the case we just have observational distribution, we have some extensions of this engine. If you have multiple data sets or multiple studies, some experimental studies, some observational studies, but this expression will be always in terms of the distributions that you have available. And then this is going to determine the interventional distribution of interest, the desired causal effect. So that's the workflow. And the question that I'm going to that I want to answer here is about what if the required knowledge is still not available? Because we started from having a structured causal model, and then specifying this causal model is really hard. Like we don't have sometimes the form of the functions, the distribution of the variables. So it's a lot of knowledge that we require to specify a structured causal model. So the theory, the Pearl theory of causation is relaxing this assumption by allowing us to do causal inference given a causal diagram. However, if you consider a high dimensional setting where you have a lot of variables, many variables, the knowledge that we have available sometimes is much coarser than what's the required to construct to fully specify this causal diagram. So how can we relax even more this assumption? That's what I'm going to answer in this presentation. So consider. Oh, this is what I just concluded, right? So Pearl's theory of causation was revolutionary because of that, because we are not requiring the structured causal model. We are just requiring the causal diagram. But it is still a lot of knowledge that is required. We need structured knowledge for every pair of variables, and sometimes this is not available. So that's the question. It's possible to relax the assumption of having a fully specified causal diagram and still be able to identify a causal effect. This is an example. Suppose that I have all these variables, A, B, C, D, are covariates for modeling the effect of this drug, is lisinopril. It's a drug that's usually used for treatment of stroke. So Y is an outcome of having a stroke. And we have, in this case, a mediator. We call this variable mediator because it's mediating the effect of X on Y. And S here is the sleep quality. And suppose that that's not our knowledge. We know that X is causing S. So the drug is causing or affecting the sleep quality. And then the sleep quality is affecting the outcome of having a stroke. But we have all these covariates, a lot of many variables, many other variables that are affecting this relationship, but we don't know the relationship among all these variables here. So the question is, given this partial knowledge, is it possible to compute the causal effect? We cannot specify the causal diagram, as I said before. So how can we identify the PY given to X in this case? The proposal is the following. Sometimes we have available this coarser knowledge at a cluster level. So we are going to cluster some variables because we don't have the knowledge to specify the relationship between the variables within this cluster. And but we know at the cluster level that some of these variables doesn't need to be all. So so in this case, I'm calling all because I'm just talking about the temporal order. So I want to avoid cycles because the theory of causality doesn't allow us to have cyclic systems. So one thing that's important is every time that you create a cluster, you know that they are following the same temporal order. And for covariates, this is usually known. For example, we know that all these covariates occur before taking a drug, the case X, lisinopril, and also having a stroke. For example, age, sex, socioeconomic status, all the medication history, some comorbidities, they are all coming before I decided to take this drug and also having some outcome of having a stroke. But we don't know. So the point is we cannot have the causal effects in the other way around. So X cannot cause any variable in this cluster. But we can have some of these variables. So any of these variables can be a cause of X of Y. It doesn't need to be all, but some of them. So it could be C causing X, B causing X, all of them causing X. Anyways, you don't know, but some of them can be causing X and can be causing Y. The other type of knowledge is about confounding. That's another type of requirement that we need to specify a causal diagram. So for example, we may know that some of the variables in the cluster are confounded, which means that I have a bidirected arrow between one of these variables in the cluster and X. For example, D, X or Y. So D is confounded with Y, or C can be confounded with X. Could be all of them. But we have this coarser type of knowledge where we don't know which variables in the cluster are affecting the other variables, but we have this understanding of some of them causing or not the variables. So one important observation is that within the cluster, any possible relationship is allowed. We could have A causing D, confounding between B and D, anyways, a lot of other relationships. So many causal diagrams are actually compatible with this current knowledge. Since we have a partial partial understanding of the system, many causal diagrams could be the true underlying diagram. So this one could be the one example where we have one variable causing X, another variable causing Y, and some of them confounded. It could be something different, A causing X, D causing Y, or any other relationships. This looks the same, right? Yeah, this is a type. But could be any configuration here, and we don't know how to decide what's the true causal diagram. Now, so how can we construct a cluster causal diagram in this way, or a cluster DAG in this way? First, we have to decide a partition of the variables. Suppose that I want to keep X, S, and Y as individual variables. So I'm going to construct clusters with only one variable. This is allowed. And all the other variables are going to be another cluster. I'm going to follow a similar construction of the diagram. In this way, I'm going to add an arrow from the cluster CI, from a cluster CI to a cluster CJ, if there exists some variable in CI and some variable in VJ where I believe that there is a causal relationship. So between the variables, we already know that X is pointing to S is pointing to Y. But now it's in the cluster level. I believe that some variables in the cluster are causing X. So I'm going to add this arrow from the cluster to X. The same, as I said, some variables in this cluster can be a cause of Y. So I'm going to add this arrow from the cluster to Y. And the bidirected arrow has the same meaning. If there's any variable in the cluster that's confounded with X, I'm going to add the bidirected arrow between the cluster and X. And the same if I believe that there is a confounding between the cluster and Y. An important note here is that we cannot accept cycles. So every time that we are constructing the clusters, they have to respect the topological order of the system. So now we have this flexible encoder of model assumptions, because we allow any type of knowledge, of partial knowledge that's available. So if we have knowledge for every variable or every pair of variable, we will have the full causal diagram or the full DAG as we had before. However, if you don't know the relationships between some variables, you can cluster these variables, and then you can now just define the relationships among clusters. And of course, if you don't have any knowledge, you have just one cluster, and then usually this is the same as having no causal diagram. Again, the clusters are created by domain knowledges, by the domain experts using prior knowledge. So usually we use clusters because of the lack of knowledge or even some consensus. Sometimes we have different theories for some specific relationships, or sometimes we have many variables, and then we don't want to waste our time defining the relationships among all these variables. If you have like a high dimensional setting where you have 1 million variables, you don't want to sometimes create the relationships for all of them. You can cluster all together, and this is even helpful for communicating better the system in this macro vision. Since the many diagrams are compatible with this partial knowledge, we can see this diagram or this cluster diagram as an equivalence class of many causal diagrams. And then every time that we are going to decide the effect of interventions, given this graph, this cluster representation of the system, we always have to consider that this has to be true for all the members of this equivalence class, for all the compatible causal diagrams for this knowledge. That's why we can, so in this paper, it is under review, but you can find it available in the archive. We extended the theory of identification of effects to consider now a cluster DAG as an input instead of a causal diagram. So we will, for example, consider these 3 inputs to the causal inference engine, and then we will have a solution every time that we can express the causal effect in terms of the clusters as units. So we don't care about the relationships among the variables in the cluster, and the expression is in terms of these clusters. So every time that we can describe this relationship, we have that the effect is identifiable. So just as an example, this is a simple example where we don't know the relationships between Z1 and Z2. That's why we put both of these variables in a cluster. And then we can identify the effect from this causal diagram. And this is the expression. I'm not going to enter in details because there's no time for that. But this is called backdoor adjustment. And this means that for any relationships that's happening between these variables in the cluster and also across the clusters, so if it's following the same knowledge that's encoded in the cluster causal diagram, then the effect will be identifiable using the same expression. So I'm just opening here the cluster Z as 2 variables Z1 and Z2, but they are, this diagram is compatible with this knowledge encoded in the cluster causal diagram. If I have a different cluster, a different diagram, but it's still compatible with the same knowledge encoded in the cluster DAG, this is you'll be identified, the effect of X on Y, you'll be still identifiable using the same formula, using the same identification expression. So that's the conclusion every time that we have identifiability from a cluster DAG. However, sorry, this is just some illustration. If this is just a simulation where we computed, this is the cluster diagram representing 10 variables. And then we generated randomly generated causal diagrams compatible with this structure, and computing the effect in the causal diagram instead of the cluster diagram. So using the true underlying diagram, we have a difference in the causal effect that's that's very small. So this is very small. It's close to 0. And increasing the sample size, we see even a smaller difference. This is decreasing with the sample size. So this is just an illustration that we can accurately compute the effects given the cluster causal diagram much that's encoding just the partial knowledge, just a much coarser description of the system. And the results are the same as if you had specified all the relationships among all the pairs of variables. And what is non-identifiability? What actually means if I don't have an effect identifiable given a cluster diagram? This means that this is a case where the effect is not identifiable. I'm not going to enter in details again. I can explain later why it's not. But this means that there is a causal diagram that's compatible with the encoded knowledge where the effect is not identifiable. This is a case where the effect is not identifiable. And the same, this doesn't mean that that the true underlying causal diagram the effect is not identifiable in this true underlying causal diagram. It is possible that the effect would be identifiable if you had specified all the relationships among all the variables. But the idea here is that we are considering a scenario where the knowledge is not available. So, of course, with less knowledge, you sometimes can lose the identifiability. So that's the conclusion. Every time that the effect is not identifiable from a cluster DAG is because there exists at least one compatible causal diagram in which the effect is not identifiable. This is just the parallel for the simulations that I showed before. So I randomly generated some causal diagrams compatible with this diagram. And just for an idea, around 85% of the diagrams, the effect was not identifiable. So we cannot, given the knowledge encoded here, we cannot guarantee that the effect would be, that the diagram would be one of these cases where the effect is identifiable. So that's why the effect cannot be identifiable from the entire class represented by the cluster diagram. If you understand a little bit more about causal identification, the machinery developed here in this work allow us to identify the effect beyond the backdoor adjustment. So the backdoor adjustment is just this one that I just showed to you, but this works for any causal diagram that you can draw using clusters. So this is a case that's called front door adjustment, and this is the expression. If you have ever heard about this name, this is the front door adjustment, and this is also extended for clusters. So we extended the entire theory, and then the idea is that doesn't matter what's the underlying causal diagram. If it's compatible with the knowledge encoded in the cluster diagram, then the effect will be identifiable using the same front door adjustment as is in this case. So these are two compatible causal diagrams, and the effect is identifiable using the same formula. As an observation, of course, different clusterings, you result in different formulas, or even sometimes the effect can be not identifiable for different clusterings. So, of course, it's a trade-off. Like you don't want to specify all the relationships among all the pairs of variables, because or is too burdensome, or sometimes you don't have the knowledge available, but that is a trade-off. In some cases, you will lose identifiability given this knowledge. It's sensible to the clustering. That's the conclusion. Going to the second part of the presentation, that is also the other end of this spectrum, where you don't have any knowledge available. So no background knowledge is available. So am I now is still available to do to infer effects? What will happen if I have no knowledge available, even for a cluster diagram, even with this more relaxed framework? Can we learn a causal diagram just using observational data? And usually we cannot, but we can learn from observational data another class of graphs or causal diagrams that's called Markov equivalence class. So all these diagrams, they are compatible with the they are compatible with the conditional independencies that are learned from observational data. So the only thing that we have available in the observational data are conditional independencies across different variables. So and there are several different, there are multiple diagrams that we can construct that are all equivalent in the sense that they all represent the same set of conditional independencies. So that's what the causal structural learning algorithms is leveraging. They are leveraging the conditional independencies in the data. So for example, a structural causal model, we don't know it, but it induces some observational distribution. So if we collect the data in a passive way, so we don't perform any, we are not running any experiment, any trial, we are just collecting observational data, we can compute the observational distribution using classical methods in statistics. And one thing that we can read from this data are independencies and marginal independencies and conditional independencies. In the case, suppose that this is the causal model, the structural causal model, we will observe that the variable x and y, they are independent, but there are some other dependencies. For example, x and z are dependent, z and y are dependent, x and y are dependent given z. So I'm just observing this set of conditional independencies and dependencies. And then the algorithm is going to learn something that represents a Markov equivalence class. So this is the representation, we usually is called partial ancestral graph, where a circle means that this could be, it's better to start with an arrowhead. So the arrowhead means that the variable that has the arrowhead is not an ancestor of the other variable. So z is not an ancestor of x, z is not an ancestor of y. But we couldn't decide, so the circle means that we couldn't decide from the observational data if this is an arrowhead or a tail or both, could be both. So we couldn't decide from the observational data what is actually the edge mark here. And why we can actually orient some of the arrows, because so that is the joint distribution, so the joint observational distribution, and we can factorize this distribution and simplify the factorization using these conditional independencies. In the case, I'm using that x is independent of y. So if I factorize in this way, I can use in this case, I can use any topological order for the factorization. But every time that I'm simplifying some terms of this factorization, I have to rely on conditional independencies in the data. So I can change or I can replace the px given y for px. And this is just a way of representing all the diagrams in this equivalence class. So there are multiple causal diagrams that are compatible with this knowledge. It's the same as before. So for example, this could be the underlying, the true underlying causal diagram, but could be this other one where I have a bidirected between z and y, could be this other one or other one. There are multiple, many causal diagrams compatible with this knowledge that's coming only from the observational data. But you can see that in all of them, the Z is, we call it collider, because all the arrowheads are pointing to Z, even in this case. So bidirected arrows or directed arrows, they are all pointing to Z. And that's why we can learn that there is an arrowhead into Z here. It's representing multiple models. And structural learning algorithms can learn this equivalence class. These are just many examples just to illustrate, and I'm using the FCI. The FCI is called Fast Causal Inference Algorithm. It's one of the classical structural learning algorithm for learning when you have unobserved confounding, and it learns the partial ancestral graph. So for example, for this first graph, I have this representation of the partial ancestral graph. If I have, for example, Z as a common cause of X and Y, I cannot learn anymore the arrows into Z. So this would be the representation of the class, which means that the Z is not a collider. It's a definite non-collider, but this could be a chain, Z causing Z, X causing Z, Z causing Y. So a chain this direction could be a chain the other direction, Y, Z, Y causing Z, Z causing Y. Could be exactly the fork, where Z is a fork or common cause of X and Y. So there are multiple models where, since they are circles here, we could be both tail or arrowheads. Anyway, there are many models represented by this class. Sometimes we can learn, for example, in this case, we can learn specifically that X is a cause of Y. This is a case where we can identify the effect of X that X is a cause of Y from only observational data, because the equivalence class has this arrow called visible. There are other cases where we can learn exactly where two variables are just spuriously correlated. So there is no cause from Z to Y to W or W to Z. So we can sometimes detect causal relationships or spurious relationships just from the equivalence class. This is just a note that we usually don't know the causal diagram. That's why we cannot manually construct the causal diagrams, but using data, we can use the FCI algorithm to learn the partial ancestral graph. And then there is another work that's also under review. It's available also in archive, where we extended the theory to now is the same engine, the inference engine, but it's now extended to in a way that now we can input the PAG, or the partial ancestral graph, representing the underlying system. So you have data, you have a PAG, you have the query, and now you can have either a solution or not, but every time that you have a solution, this means that you have an expression just in terms of the observational distributions available, determining the desired interventional distribution, and using only the representation coming from the PAG. Again, some examples. If this is the PAG, this is again the backdoor adjustment, because it's just for simplification. This is learnable from data, so we can learn this representation entirely from data, and we can identify the effect of X on Y as being this expression just giving the PAG. And this means that if this is the causal diagram, so this is a possible causal diagram for this, that's a member of this equivalence class. If this is the true causal diagram, then the effect will be estimated or computed using the same formula. It could be another one. This is another causal diagram compatible with this knowledge in the PAG, and the effect is again identifiable using the same expression. So every time that the effect is identifiable in a PAG, it's identifiable in the entire Markov equivalence class using the same identification formula. And what is non-identifiability? So this is an example where the effect is not identifiable. So this means that there exists some graphs where the effect is identifiable. So for example, this could be one graph. This is a graph in the equivalence class, and the effect is identifiable, but I don't have the knowledge to know that this is the true underlying graph. I just have the peg. And the peg allows me to construct a causal diagram where the effect between X and Y is not identifiable. So this is another example that belongs to the equivalence class, but the effect between X and Y is not identifiable. So that's the meaning of no identifiability in a peg. So to conclude, the language of cluster DAGs, it's relaxing. It's a way to allow us to describe partially understood causal systems. So it allows us to construct knowledge-based graphical models. And this is important when the structure is only partially understood, so we don't have the knowledge available, or sometimes when we have competing explanations for the relationships among the variables. And sometimes the concepts are just better expressed by groups of variables. So we have this concept of macro variables. And in the other side of the spectrum, we have the structural learning algorithms, where you don't have any knowledge available, but you can use data, observational data, to recover the equivalence class of the true underlying model. And we have developed sound and complete algorithms for identification of the causal effects from given either C-DAGs or cluster DAGs and pegs that are the partial ancestral graphs. Of course, there are still limitations. So the construction of a cluster DAG currently is entirely based on prior knowledge. And the peg, on the other hand, is based entirely on data, on observational data. In one side, in the cluster diagrams, the non-specification of the relationships among variables that are in a cluster, that are clustered, they can make some of they can render some of the effects non-identifiable, because not only between the variables within the cluster, but also sometimes also between the clusters. And again, from the observational data, not always it's possible to decide the causal relationships between some pairs of variables, particularly in scenarios where we have hidden or unobserved confounders. So our next step is now developing an algorithm where we can learn the equivalence class of C-DAGs, combining both observational data. So instead of just using prior knowledge, we want to combine also observational data and the knowledge that we can that's describing partial order among clusters. So this is a challenging open research question that I'm working on right now. So I'm happy to take questions, and thank you very much for staying here with me.
Okay. I have a problem with the microphone. So thank you, Adèle, for this nice talk. So I will open for questions. So guys, feel free to ask questions in Portuguese to Adèle if you have some, or just write on the comment box so Adèle can read or can translate, no problem. So I have a question about the cluster graph that you comment, because you said that the clusters are construct with the expert on the area that you are studying, or the area that you have the data. So for example, so we construct the cluster with the variables that we don't know the edges between these variables, right? So the variables that we don't know the edge between the variables, we put together in a cluster. So I was wondering if we have two clusters, so I need to have at least one edge that connect these two clusters. This is right?
Is it right? Yeah.
Otherwise, I should put all the variables together.
Yeah, let me get an example where I have two clusters. This is one, but I want something simpler. I think I have here. So yeah, so suppose that I don't have the knowledge between A and B. the arrow between A and B. So I have to put them in a cluster, because it could be A causing B, B causing A, or bidirected between both, or everything together could be bidirected and some directed arrow. So I don't know this knowledge, but I need to know the relationships between these variables, at least with in terms of partial order. So that is a question of partial order here. So to connect two clusters, I need to know that that exists at least one variable in this cluster that's connected to another variable in the other cluster. For example, B could be connected to C, and no other variable in the second cluster is going to be a cause of the variable in the first cluster, because I cannot create a cycle. Okay. So you need to know the partial order among clusters to create these clusters. And you can do this manually. Like you can, for example, you can start with two variables. So these two variables are not connected. Sorry, these variables are clustered because I don't know the connection, but I need to know, is B a cause? Now it's a potential cause. So could B be a cause of C? Could B be a cause of D? I don't need to know, but if it could be, I add this arrow from the cluster AB to the cluster CD. And I have to ask again to decide if the cluster is admissible. So there is a question about admissibility of the partition. So if there is any variable in the second cluster that could be a cause of A or a cause of B, I would have to add an arrow from this cluster to the second, to the first, right? Because that's the way that I'm constructing. Every time that I have one variable in one cluster that's potentially a cause of the other variable in another cluster, I have to add the arrow between the clusters. Mm-hmm. But if I have a case where I have to add both an arrow from the cluster 1 to the cluster 2 and an arrow from the cluster 2 to the cluster 1, this would create a cycle. So this has to be, now in this case, or you create a different clustering, like you have to know what are the potential variables that are cause of the first cluster to add a third cluster, or you have to merge both of the clusters as just one, because then you avoid creating cycles. And this is exactly because your knowledge doesn't allow you to create these two clusters. You don't have enough knowledge to create two separate clusters. You need to create just one. Your knowledge doesn't allow you to decide what are the variables that are following this topological order that's consistent with the causal model. Mm-hmm. You understand? Like, yeah, it's less knowledge than constructing the DAG, the full causal diagram over all the pairs of variables. So it's a relaxation, but there is still this knowledge about partial order that's required.
Mm-hmm. Right. Thank you. Mm-hmm. So any other questions? Okay, I have go ahead, Julia. Please.
Let me ask Adèle. First, thank you for the clear presentation. And I would like to ask about how much flexible these results in terms of learning causal graphs is in terms of latent cluster. When you don't have information about variables including in the cluster, and then you can to search your space, your observable space, but including position and information about latent cluster. I think it is very flexible manner to learn these graphicals.
I'm not sure, like, I'm not learning. So right now I'm not using any algorithm to learn the clusters. So this is what I said that I'm working right now. So this could be an interesting route to follow, like using latent latent representation of the variables. I think that's what you're saying. Like instead of like you want to learn, I don't know, maybe using factor analysis or something that can learn a latent representation of the variable. So this would be a cluster or a variable representing several variables at the same time, I guess. And this would allow us to help to know what are the variables that are together. So this would be just a tool to help us to understand what are the variables that are clustered together, or because they are highly correlated, or but it's different, right? There is a so the cluster is not latent. Here we want to create clusters over the variables that we have available. So we have all the variables here, they are observed. We could have like each bidirected arrow means another set of variables that are latent and are causing both clusters. So learning this latent cluster, it's a different thing. Like it's a different approach, I guess, because then you would turn one latent variable as being one. Like you could use techniques to have a value or some representation for this latent cluster that's here, but it's something different. Right?
Okay.
I don't know if I answered the question.
Yes. And what about the generalization of these results for not independent observations, but clusterization? For example, family data that I am very interested.
Yes. So all these algorithms that I mentioned before, the classical one is the PC algorithm. The other one that allows hidden variables is the FCI algorithm. They work under the assumption that the observations are all independent. So it's IID data. And it would be very interesting to have, but one thing that's important to understand is that these algorithms are just learning based on conditional dependencies that are observed in the data. So you need a conditional independence test to read these conditional dependencies from the data, and then use the conditional dependencies to learn the representation of the equivalence class. So when you are applying a conditional independence test, there is this assumption about the data being IID, the observations being all independent of each other. But if you want to extend, you want to extend by creating or developing a new conditional independence test that allows, for example, correlation among members, relatives in families. And then for the case of clusters, this would be very interesting, because now the conditional independencies is no longer between two variables, it's between two data sets, right? So each cluster here is a set of variables. So how can I decide that a set of variables is independent of another set of variables, giving a third set of variables? So there are some tests that allow us to compute conditional independencies among data sets. I believe the mental test, right? Then extend the mental test for family data would be very interesting to now apply learning of these cluster diagrams from data when the data is, there's correlation among families, for example.
Okay. Okay, to me, it's very clear.
Okay.
Thank you.
So, any other question? So, since we don't have more questions, I would like to thank you, Adèle, again for this really nice talk. So, thank you, Adèle.
I hope it was